The scanner system, like I said, the scanner, a robot, which just which we use to move around a small antenna, a near-field probe, preamplifier, a spectrum analyzer. It doesn't have to be a Tektronix. We can support almost any brand, and a PC. And these are the components in the system. And what we do is that we scan a grid of points above a test object lying on the scanner table. And we use a spectrum analyzer to measure the whole frequency spectra, and we import it into the PC, and this allows us to make these color field plots that help users see hotspots, find EMI sources. And what's it good for? Well, the use cases, we have three main use cases. The first one is when if you are developing a product that needs to be tested at the end in a test lab at 10 meters or so. And this system allows us to, preferably in early stages of design, take a kind of photo, EMI photo of the board. And what you see here is 6 measurements of the same PCB, the same frequency, everything is the same except the value of one decoupling capacitor located here. And you can see in this measurement we had no decoupling. In this one we have just a very small one, a little bigger more, and you can clearly see the difference, what actual effect the change had. And this is how it works. This is what customers do. They measure and they change the DUT a little bit and measure again, and then just compare what happened, what was the effect. Because this is actually what we do. It's a probe and a spectrum analyzer. People have been using this kind of probes and spectrum analyzers for like 50 years to hand sniff to find sources, and it works. You can find a source using just a spectrum analyzer and a handheld probe, but the problem comes when you try to repeat the measurement. That's where we need the scanner to make it repeatable, and the software to document and to visualize. But this is the thing, objective measurement, objective comparable measurements. Looking at the hardware, we have 2 scanner series. The SCN series scans with 0.1 millimeter step size, and that is enough for almost everyone. Only companies producing like IC manufacturers, or maybe cell phone manufacturers, or hearing aid manufacturers, and if the product is very, very small, then maybe you need this higher resolution. But I think 95% will be covered by the SCN series. The SCN series comes in 4 different models. It's a 2D version, a small, fairly cheap one, measures 200 by 100 millimeter, and a small one, but with the 4-axis, this module, which moves the probe up and down and rotates around the probe axis. But the most common scanner we sell is this one, the SCN 534. It measures 300 by 200 by 100 millimeter, and it rotates the probe. We also have a big one. If you have really large test objects, we have a bigger version called SCN 564. With all of these models comes a probe kit and a preamplifier for either 3 or 6 gigahertz, and you can even upgrade to 10 gigahertz. We have some options for the SCN series. We have the DUT camera. I will show you that in just a few minutes. It's for photographing the DUT and aligning it with the measurements. We can also measure immunity. It's a software option, and I will tell you about that one closer to the end of the seminar. Beacon calibration. It's this blue box down here. It contains 3 small beacons, and it allows us to very accurately calibrate the X-Y position of the probe, not to the physical center of the probe tip, but to the electrical center of the probe tip. This is necessary if you want to do very, very accurate measurements. Normally, if you measure like 1 millimeter steps, something, you probably will not need this one. But if you want high accuracy, this is really good to have. Probe calibration strip line. It's this one. It's a strip line board that we use together with a spectrum analyzer with tracking generator, and it allows us to co-calibrate to scanner system, for example, in different parts of the world, where you want to know for sure that both systems measures the same amplitude frequency. We have the upgrade for the 2-dimensional scanner that adds this ZR module, so it becomes a 4-axis. We have a shielding tent, this one. This is for protecting the measurements from outside interference. Normally it is not necessary, but if you are located in a very hostile environment where lots of radio in the air around, maybe you will need it. And we have a transport case, this one, a real sturdy case that with wheels, so you can easily transport it. You don't have to worry about sending the scanner on a lorry or a plane. It will protect the scanner really well. And we also offer a spectrum analyzer, Tektronix RSA 306B. The high resolution scanners, like I said, has 25 microns step size. It has a built-in beacon calibration at the back of the scanner table around here. And the measuring cube is 39 by 28 by 13 centimeters. It comes in 3-dimensional or 4-dimensional, where the 4th dimension is rotating the probe around its own axis. It comes with the same probe kit options and preamp, and like I said, this is mainly for companies producing very, very small things. We have some options for the high resolution scanner. The IC option contains a very small probe, rather the probe tip around here, it's very, very small, and it allows you to measure very accurately, for example, inside IC. We have a camera so we can see these small things, and we have some lighting also. The probe kits, this is what they look like. No matter the frequency, they contain these components. We have a low frequency magnetic probe that picks up field from below. It's a loop, a horizontal loop, and we have one high frequency magnetic probe with a horizontal loop, and then high frequency with vertical loop. This one makes sense to actually rotate around the probe axis, so can pick up field from different directions. And we have an high-frequency electric probe. This probe will also be the one you use if you are doing immunity measurements, because it can take more energy than these very small probes, because the wire inside here is like 0.3 millimeters or something, so it cannot take too much power from a signal generator. We can not only measure on PCBs, we can measure on cables. Also, here is an example where we measured 3 different versions without a ferrite, with using a ferrite with the cable 1 turn, and with the cable 2 turns on the ferrite, and you can clearly see the difference. We can also measure the sides of a box, because we do not only scan in XY plane, we can scan in XZ plane or YZ plane. And this is just to show you the level of detail we can achieve when measuring 0.1 millimeter steps on a small IC. Let's go to software. Okay, here we are. The software is divided into tabs. On the config tab, we need to tell the software what kind of spectrum analyzer we are using. And we have drivers for most common spectrum analyzer brands and models. If you have one that we don't have on the list, we are happy to try, but we found that the real low-cost versions of spectrum analyzer, they can be difficult to make drivers for, because I think they don't put a lot of effort into the firmware of those spectrum analyzers, at least not when it comes to remote control. So, but anyway, we will be happy to try if you have a spectrum analyzer that you want to use together with our scanner. We have some spectrum analyzer settings. 4 of them are predefined, but you can easily make your own setting by just typing in a new name. Let's call this one my own setting 2. And we save it and close, and you can see now that it is in the list. Looking more closely at the settings, we don't use a lot of brand-specific features, just standard basic spectrum analyzer settings really. It's mostly about frequency range and resolution bandwidth, but if you use one of the 4 predefined settings, it will work. Then you can tweak them if you want to do something else. One setting is worth mentioning, that is the number of spectrum sweeps, because not all signals on the PCB are always there. For example, if you measure on a bus or something that comes and goes, we may have to stay a while in every measuring position, taking a number of sweeps just to make sure we actually catch the signal we are looking for. About the probe, we can enter antenna correction factors, but honestly most people don't, because this is all about relative measurement, and since we are comparing the difference, so any compensation will be kind of cancelled out when we look at just the difference. But if you want to add antenna correction factors, you can do it. We support actually still in the software some older scanners. So if you have an older scanner, you will at least benefit from the newest version of the software. There are some more settings on this tab, like things that you only need to change once, probably. So I've hidden those, so not to clutter the user interface. And here are some wizards. Beacon calibration wizard shows you step by step how to do that. Also strip line calibration, the option I mentioned, step by step how to do that. But let's move to measuring points. We need to define the area that we want to measure, and to do that more easily, I have on my scanner setup, and the setup is this. We have the scanner, and up here you see the camera, and we have the spectrum analyzer. And I want to show you now the DUT camera option. I click this button, and the scanner moves to, actually it was already in photo position, and we take a photo, and the software asks, please enter height for photo alignment. This is because we need to compensate for the perspective view that the camera has. So we need to tell the software the height of the PCB, and my PCB is approximately 10 millimeter. We enter the 4-point alignment automatically filled in. This can be done without the option, just taking a photo with your cell phone and using this 4-point alignment feature, and it will bring in the photo aligned with the coordinates on the scanner table. So now we have a photo as background, and I will just click and draw an area here like this, and I say this is 25 millimeters tall, and if we look at the scanner path, you can see it moves in a pendulum-like movement, and in every measuring point, in every cross in this grid of points, we measure. And how we measure, I will tell you now, because on the Measure EMC tab, we have 3 types of measurements. Pre-scan is the simplest measurement. That it will only result in this trace from the spectrum analyzer, this graph, and this list of peaks. And what we do is that we put the spectrum analyzer in max hold mode, and then we just scan the board, and amplitudes will accumulate on the spectrum analyzer, and then we just dump it into the software. So this will not tell you exactly where on the board you have peaks or sources, but it will tell you the worst case on the board. We can select a few of these peaks, add them to this list of frequencies to measure, and we do a scan measurement. And this is a narrow band measurement that this will produce 3 measurement files only showing these frequencies. And it will give a color field plot that you can see exactly where this particular source is. But the most commonly used measurement is multiscan. Multiscan is actually a pre-scan done in every measuring position. And why don't we, let me just double check in the settings. We have this one, and we have the measuring points path like this. So let's do a measurement. And I will save the measurement here. Yes, overwrite. Okay. and the scanner is moving. Going down to the first measuring position, we're resetting the spectrum analyzer. And let's zoom in a little bit. You can see the probe moving, and if we look at the spectrum analyzer, you can see we take 3 sweeps and then we reset the trace, so every measuring position is separate. This is a 10 millimeter measurement, and it will take approximately total time 1 minute is 10 millimeter. Of course, if we scan with 5 millimeter steps, it will take 4 times as long, but the best way to approach a PCB, a product that you don't know anything about, is to first make a fairly rough scan, for example 10 millimeter steps, and when you see where on the board you have some interesting areas, you zoom in and measure with smaller steps just in that area, because scanning a wide area with 0.1 millimeter steps to start with it's not efficient. Okay, and the measurement is done. Let's go to View Scan tab and open. Let's see where we are. Here we are. This is the measurement we made, and I will also open the same background photo that we made earlier. Now you see we have the PCB photo and we have the measurement, and up here we can see accumulated trace. This is actually the max hold sum of all the measurement in every measuring position. So this is basically the same as what we saw here when doing a pre-scan. And up here we can click to regenerate the field plot, so we can analyze any frequency we want afterwards. And the amplitude is shown in a color scale here. It is also shown in 3D. And if we are interested in this position only, we can look at the trace data from the spectrum analyzer just from this measuring position. Let's say we have 2 measurements, one that we made in the beginning of our little quest, and then we changed the DUT a little bit. Perhaps we added some filtering or whatever, and then we made another scan. So I will just pick one other measurement. What I do now is I hold Control key and I just click with my left mouse button and I move the measurement to the side, and now we can very easily compare one before and after measurement and clearly see the difference. And if we change frequency, both measurement will be updated. This is one way to see the difference between before and after measurements. You can also calculate. We can subtract one measurement from the other and produce a third that is only the delta. But I think most customers are happy just looking side by side to the measurement, and this is what it's all about, to be able to see the difference. And if you do this in early stages of design, when it still is cheap to make the changes, you will save time and money in the end. If you come back from the test house with a failed result and you know what frequency, but you don't know where it is or what to do with it. Of course, the scanner can help you there to make a field plot and tell you where the source is. But chances are that if you got that far in the process, then you have to use expensive solutions like far-right and shielding boxes and so on. While had you been using the scanner from early stages, maybe it was just a cheap capacitor in the correct place or a grounding, or so you will save time and money by not having to go several times to the test house. Also, a use case is to for improving internal quality. For example, a cell phone contains a bunch of modules, and these modules can interfere with each other. And to increase your quality, your performance of your product, you need to keep track of these modules and how they interfere with each other. The third use case is as a quality assurance tool in production, where you can, for example, if you use a component from a second source, you can compare a scan of the product using the second source component with a known good, like a master version of the product. And I mean, really, if you change your product with a different component, you should really go back to the test house and test it all again. But nobody does that because it takes time and expensive and so on. So what do? You do the best you can, and if you can make an objective, comparable measurement using the scanner, I think it will help. Okay, so we looked at some settings, spectrum analyzer settings mainly, and how we make measuring points and define those. If we have high components, for example, this cooler and this capacitor, we can make an island around those, and we can say that we need to go up to 40 millimeters. So the probe will skip over these high components. And since we have several of these levels, we can build a fairly complicated model of the DUT just using this general measuring points generation method. However, if you have more complicated DUTs and really need to measure very closely, we can import a 3D model in STL format, which is the simplest form of 3D models, and every CAD system can export it. So we import this one, we align it using either this 3-point alignment method, where we point at 3 points on the model, and we tell the software the real coordinates of these points. Or a simpler way is to just move the model step by step until it aligns with the position of the DUT on the scanner table. We can rotate also, of course. So to generate measuring points path on a 3D model, we tell the software X and Y, start and stop, and we say a step size and a distance to the surface, and we generate. And now you can see that we measure at a fixed distance from, let's go a little closer and regenerate. So this is one way of doing it. We can also use the this little guy, the laser distance meter, to actually build our own 3D model to scan topography of the DUT. it works the same way. You just import it here. You click on this measure heights using LDM, and you will get a 3D model of your test object, and you can generate the same manner. You see here rotation around probe axis. If we are using a probe with a vertical loop like this, it makes sense to rotate it in every measuring position so that we get the worst case, and this is done in this area. Same you can do if you do this 2.5 dimensional way of generating the measuring points. Okay, what else do we have? Settings, measuring points. We talked about the measurements. We can also measure emission over time. Just say for how long, what frequency, and at what position, because this is just one spot. And we use this to document if, let's say, the test object goes into different modes, what happens with emission then, or temperature when it gets warm. Does anything happen? Could be interesting. And we can load several of these measurements and compare them, the graphs here. We have this tab to view several pre-scans or multi-scan accumulated trace. We have a limit line since this is relative measurements. Of course, the limit line is also relative. We talked about view scan and calculate. We can also do batch measurement. If you, for example, have several test objects on the scanner table, you can make separate measurements of them overnight if you just set up settings, measuring points path, and give it a result file name here. Or if you have the need for frequencies, separate bands, frequency bands that you want as separate measurements, you can also use this feature for that. Okay, so let's move back to the PowerPoint. And I wanted to show you a little video of the laser distance meter. You can see a red laser dot that measures the difference, and this is the model created by this feature, and it allows us to measure at the fixed distance from the DUT. And this is a measurement. This is what it looks like. You can see the measurement follows the model, and we can have a photo overlay to see better where the sources are. Okay, immunity. Immunity is the opposite. Instead of a spectrum analyzer measuring what comes out from the DUT, we use a signal generator to push on energy, and we use something called error detection device to figure out if the test object is failing or not. And then we generate the same type of measurement as the multi-scan, but it will show sensitive spots instead of radiating spots. This EDD, the error detection device, is an instrument of your choice that measures some signal from the DUT that can tell us is the test object failing or not. And what we do is with the signal generator, we move to the first frequency, and then we ramp up amplitude until we get failure, and then we take the next frequency and we ramp up amplitude until failure, and this is how we build a trace that will be right on the limit where tells us the amount of energy needed to make the test object fail. The EDD can be any instrument. It needs to be VISA compatible. We need to be able to talk to it. and you need to actually provide one Skippy command. In this detection sequence, we need one command, one question, and this question needs to be answered with a number, and this number is then compared with this mask, and this is how we find out if the test object is failing or not. I will show you a video where my stripline board is device under test, and the spectrum analyzer here is connected to this stripline board and acts as an error detection device. And I set it up so that if the spectrum analyzer measures more than 50 dB microvolts, we will consider that to be failure. And then we have the signal generator connected to the probe. And this is how it works. We move to the first measuring position, and then we start moving frequency and amplitude, and all the time we measure the health of the DUT. And I will zoom in a bit. Here we are. You can see we change frequency and we change amplitude, and this is the result on the error detection device. You see the peaks stop at 50 dB microvolts. Yeah, and this is how an immunity measurement is done. Let's skip that one. Automation. Many customers ask about automation. We don't have a full-blown API yet, but we can do batch measurements, and we can do them on command from another software. You can actually call the software with the batch number, the parameter, and it will run the batch and then close the software. Also, for automation purposes, we have a small software called Mesh2JPEG. It will take a measurement file and a list of frequencies, and it will produce a bunch of these field plots. And this can also be run from another software. Here we have some features in our latest version. The DUT camera you saw. We also, well, let's move past that one. We also have new is a simple 3D editor that allows us to give some extra space around the 3D model, because if you import a 3D model from your CAD department, chances are that it contains PCB, components, connectors, but not the cables or other stuff that you need in real life when you put the DUT on the scanner table. So to allow for some extra space that you may need in real life, you can just click on a point on the model and you edit, change the height, for example, and you can also make that height spread, one step out, 2 steps out, 3 steps, and so on. So you can make room for real world components that you need. Further probe extension. This allows us to measure deep down the sun is destroying my camera. Hang on. Okay, better now. You can see that the probe extends maybe 7-8 centimeters or something, but if we are to measure down between boards in a rack, for example, of these boards are like 10 centimeters tall, we need longer extension, and that is what this new feature allows for. It will reduce the Z-axis movement, but if you have the big scanner has a 300 millimeter Z-axis movement, then it's no problem to gain extra 5 or 10 centimeters probe extension. Probe tip compensation. If you are to measure very, very close to a 3D model, you may need to compensate for the diameter of the probe. And you can see here, this is no compensation, this is with 3 millimeter compensation. And this is just to make sure that we do not touch the DUT with the probe tip. This is only useful if you want to measure very, very close. Normally this is not necessary, but if you need it, you have this feature in the software. Two-dimensional scanners can now measure inside a box and then go allow time to manually move the probe up and down, because we pause the measurement at the first measuring point and at the last measuring point. So now you can measure inside a box also with two-dimensional scanners. We have a check for updates feature in this one. So if there is a free of charge update available, or there is a feature version released that you may benefit from, you get notified in the title of the software. It requires internet connection, and you can ignore it. Everything will work just as it always has, but you will get notified. So now, I guess it's time for questions.